So today we're going to start putting topics together, kind of like you're going to begin to see overlap in topics, and this is pretty common. And a lot of your long free response questions are going to be multiple topics tied into one. So in this first little scenario right here, we have 3 different cases, and this is going to tie a little bit of thermochemistry to equilibrium. It's super simple. So you guys remember these from Thermo. Case 1, what could you tell me about case 1? What type of reaction is that? Bree? Yeah, it's exothermic. Case 2 then we know is endothermic. And then in case 3, there's really no change in heat, so the delta H is 0. But we can tie this to the magnitude of K. Now, there's not absolutes. We have to take into account entropy, which we're not yet. But in general, if the reaction is exothermic, normally, one of the reactions, forward or reverse, if this is an equilibrium system, is going to be favored. If I asked you which hill you wanted to run on case 1, the forward hill or the reverse hill? Because you're a runner. So no, anybody but Matthew, what would you prefer to run? I would prefer to run the forward hill. The forward hill has lower activation energy, right? So due to that fact, forward is going to be favored over reverse. Remembering that K is products over reactants, if we favor the forward, we're going to produce more products. So what's the magnitude of K of most exothermic reactions? Greater than 1. Okay? Which hill would you rather run here, the forward or the reverse? The reverse, meaning the reverse has a lower activation energy, so that's going to be favored. Again, products over reactants. If the reverse is favored, we make more reactants, so the magnitude of K is less than 1. You will see a question like this on the test. Okay? So here, what would K be? Equal to 1. Right? Not a very common case. But again, these are not absolutes, but for the most part, exothermic reactions have a K greater than 1, endothermic reactions have a K less than 1. All right, that's our tie to thermo. Now let's do a tie to kinetics. So you again are going to have to be able to write rate loss from the mechanisms. We already know how to do that. So let's go ahead and write what we used to think was the rate law for this reaction. You go to the slow step, and what do you write? Rate is equal to K times slow step C to the first. Okay. Well, that's okay, but we have a problem. We did not run into this problem before, and you weren't ready for it at the time we first learned them. Can anyone see something interesting? I'm supposed to be able to measure that C in order to change the rate and use that rate law. What's going on with that C? What? It's an intermediate. Do you see how that C is made and disappears? The C does not show up in the overall reaction, so it's nothing that we can measure or observe. When that happens, we have to do something called an equilibrium substitution. We have to take the relationship between this and define this in terms of something that we can understand, something that shows up in the overall reaction. So, first thing we're going to do then is go to the equilibrium step and write an expression of K. What is Kc equal to if we're looking at the equilibrium step, which is always going to be before the step in question? Concentration of C divided by concentration of A times concentration of B. So remember, C is our culprit. C is what we want to replace. So I'm going to rearrange this equation in order to isolate C. Whatever it is we're trying to replace, we need to isolate it. So if I just cross multiply, I get the Kc times the A times the B, and that's equal to C. So all I need to do is take this, plug it in to there. And so let me just show you what happens. Rate is equal to your K times your KC times A times B. What's a constant times a constant? Another constant. So when you rewrite this, all I really need from you is just to write something like K prime or something. So I know you know it's just a different constant. Times A times B. And this then is your final rate law. Let's do one with real chemicals. This one, number 15. Nitrosyl bromide. We have a mechanism. First thing to do is determine the rate law. Let's figure it out as it's supposed to be. Rate is equal to K times what? NOBr2 to the first times NO to the first. All right. I'd say this was a good rate law, but we have a problem. NOBr2, it's an intermediate, right? Whenever you have an intermediate, you have to replace the intermediate. So this is our culprit. We can leave NO alone. We got to replace NOBr2. So go to the fast step, write your equilibrium expression. NOBr2 divided by NO times Br2. Remember to isolate the culprit. It's that guy. We want to isolate him. So I'm going to cross multiply K times NO times Br2, and that's equal to my culprit. So now I can take all of these, plug them in to there. So rate is equal to, I'm going to combine my K's and make K prime times NO times Br2 times the original NO that was there. So let's clean that up. What is rate equal to? Beautiful. K prime times NO squared times Br. So if you're asked the order with respect to things, it's after you do the equilibrium substitution. This is the correct order. So, sorry, I'm eating Slam and Dunkin' people at home. So it's probably really loud in your ears. But anyway, do y'all remember the method of initial rates problem, that super hard one? The 3 I told you to do, that you could try, and it had a coefficient that was a half. This next problem we're going to do is showing you where that comes from. It doesn't mean there's a half a molecule slamming into each other. It means there's going to be some sort of relationship in a step prior. And so this is going to be an example of that. So our slow step then, we write the rate law. Rate is equal to K times Br times H2. If you look at our two reactants, notice that Br is going to be your intermediate. So this is the culprit, needs to be replaced. So we write a Kc for the equilibrium step, which is going to be prior to the slow step. So we get Br squared divided by Br2. If we cross multiply, we get Kc times Br2 is equal to Br squared. Can we put Br squared into Br? They're the same thing. No. So what do we have to do to get Br isolated? Square root. So it doesn't, it's a constant, it doesn't matter. Times Br2. We know that to the half means square root, right? Is equal to Br. And that is what we substitute in. And that's where we get our weird halves that tend to pop up now and then. So rate is equal to K times Br2 to the half, K prime, times the original H2. So when you see a half, basically what that's saying is due to the fact that this is a 2-to-1 ratio, half of this concentration is basically equivalent to the Br. And so that's what we're equating in order to place into the rate law. So pretty easy. There's another one listed, but this one was the hardest one. I don't think we need to do another one. But that's it for this little bitty lecture. We're about to start a quiz, so you got about 5 minutes to study.